Welcome everyone. In this video I'm going to do another freezing test, and I will test the TEC12706 Peltier cooler. So I already tested this unit for the minimum temperature, and I was using a regular CPU cooler with heat pipes and a lot of fins and 2 fans. But here I will be using, as you can see here, water cooling, and I have the Peltier in this bathtub, or it is under it. So we will cool this aluminium tub, and also I will add 100 grams of water. I measured this and it should be around 100 grams. And I will measure the temperature by using my freshly built temperature logger. It has 4 sensors and they are waterproof, so I can really use them in this experiment. The only drawback is, for example, as compared to a K-type thermocouple, which is here, is the size, and that causes 2 kind of headaches for us. One is that just the physical dimensions, so I can put this to more tighter spaces than these things. That's one of the problem. And the other is that their sheer mass is much higher than or much larger than a small piece of wire, which causes them to be a bit more sluggish when it comes to the temperature changes. So these things pick up the changes much slower than a very tiny piece of wire. So it's not a problem. I will use this. It has an SD card slot here, and the SD card is already in there. So we will be logging the data on the SD card, and then I can provide you much nicer data. So I will use this, and I will put all these sensors somewhere. I don't know yet in which order, but probably these 2 will be in this tub, and then another will be immersed in a spot which is not visible, but that will be in that corner, and that's the tank of the water, and it comes out on this tube. Here we will measure that temperature, the outlet temperature again, and this is a flow indicator, and the thermometer will show the data here. So this tube goes there, does a circle, goes through this valve, and goes to the tank. So we will measure the temperature roughly, let's say 30 centimeters from here. It goes there and then it ends up in the tank. And then I think I will use this last piece at the other side of the radiator. So I will check what is the temperature of the air which is leaving the radiator. And the cooling is there in that direction. I installed the fans as usual in a push configuration, which means that the air is pushed through the fans, so the exiting side of the fans are facing the surface of the radiator, and the fans are pushing the air through the radiator. So you can see that I have the banana plugs for the Peltier units. Here is our power supply. What I will do here, and it's very important, first of all, this K-type thermocouple will be put, I will put it in this channel. So I don't know if you can see it, but there is a small gap because of this channel. So I will just put it in between this water cooling block and the channel. I will try to bend it in a way that it will like push it, it will be pushed against the back side of the water cooler block, which means that we are like indirectly measuring the hot side. That's a very important parameter, as we know. And then the whole thing will be surrounded by this cloth. So I just folded it up, and let me just, so it will be something like this. And of course there's another. Now I'm not doing it for real, I just show you how I will do it, but I will do it properly. So this will be surrounded nicely, and then we have this polystyrene block that will come on this, and I will put on a plexiglass on the top. So there is the hole, and you see 2 holes here. So I will insert the sensors through those holes, and then another piece of cloth. I will just roll this up in some way and then push it in. There won't be any convection, but this is just an extra step of taking care of the unwanted heat transfer. So let me just quickly set up everything, and when the water is running and the equipment is running, I will come back to you and we will start the experiment. So now, as you can see, I have assembled everything, and I also changed the camera a little bit for you, so you should be able to see a bit more things, and so there is a larger field of view now. So you can see the thermometers are already running. We are not logging the temperature, we are just measuring it. So I just want to quickly repeat what is going on here. So we measure the temperature at 4 different places. There are 2 sensors in the bathtub, the channel 1 and channel 2. I know you cannot really see it, but I will log the temperature and I will put the chart on the video, so you will see the temperature measured at every second for the whole experiment. So one will be on the top part of the tub and the other will be here. I took a picture of this from a closer perspective, so you will see that picture and then you have a better imagination about the thermometers. And then temperature number 3 is in this tank here. So basically it is measuring the hot temperature which leaves the water cooling block that is cooling the hot side of the Peltier cooler. But of course that water goes for like half a meter before reaching that thermometer, so of course it gives off some heat but not too much. So that's the water temperature, and the channel number 3 should be relatively close to this thing here, because this is also measuring the water temperature which is coming out from the hot side, and that is located here. So the thermometer cable is this one, this thin wire, and then this is just a flow indicator. So it doesn't measure anything, just spins and shows you that the water is running. And the 4th temperature is on the other side of this fan or this radiator. So the fan is pushing through the air, the fresh air through the radiator. The air picks up the heat from the radiator, which is at a higher temperature than the ambient temperature, and then the hot, let's say hot air, leaves the other side of the radiator, and that is the place where I measure the channel number 4. So this is behind the channel number 4 is behind the radiator, roughly like halfway at the height of the radiator, so that should be fine. And then, as I said, this K-type thermocouple is attached to the back side of the water cooling block, so that is also something like a hot side temperature. And just a few sentences about the route of the way of the water. So let's say we are starting in this radiator. So the water comes out from the radiator and it goes through the pipes, which is this clear pipe running down here, and the water, which is like freshly cooled, is directly entering the water cooler block on the, let's say, cold side. So it goes into the water cooling block, it goes through the channels, it picks up the heat from the hot side of the Peltier cooler and then comes out, and then this is roughly like 5-6 centimeters from the hot side of the block. So then we measure the temperature here, we do a circle here, and the valve is here. We go up, and then from here, roughly in 30 centimeters, we reach the water tank. And then the water goes out from the water tank and then goes into the radiator, and the whole circle is being repeated over and over. So that's what we have. So what we learned from the 6 ampere unit is that the minimum temperature is somewhere around -21, -22 degrees Celsius, and the corresponding current where I could reach that minimum temperature was 4.8 amperes. So what my idea is now to apply 4.8 amperes on this circuit and see how long it takes to get to the temperature, which is the 0 degrees Celsius. And then I just leave the system to run, because now I can log the temperatures. Because what we will see here is that the water is being cooled down to from room temperature, which is roughly 27 degrees now. It goes down to 0 degrees Celsius, and then the phase transformation will start around that temperature. So the water molecules will start to go into the solid phase, and then this will need some extra heat, basically, which is the latent heat, and we feed that or we remove that excess heat by using the Peltier cooler. And after that phase transformation is finished, then we can cool the ice below 0 degrees. But as long as we have the two phases present in the same system, so we have liquid plus solid, we will be stuck at 0 degrees. So basically that's all. And one disadvantage of this system, I just cannot make anything to improve it right now, is that the water is not stirred, which means that the heat conduction within the water can be somewhat bad, and then the temperature is not reached in the way that I want. So the optimal experiment would be to have a tank where I can stir the water, and then that means that the heat is equally distributed in the whole volume of this 100 grams of water. But hopefully it will be still useful for us. So now what I suggest, that I should turn on the power supply. I should use this power meter, or sorry, ampere meter, to measure the current which is flowing through the device, and then we start our experiment. So I turn on the data logging, and then I start the power supply, and we see what happens. So now I measure the things. Power supply is on, and we go until 4.8 amperes. And I almost forgot to measure the voltage, so I will bring the voltmeter as well. So here is our voltmeter, and I'm just attaching the clamps to the Peltier cooler's power supply connection. So 12.74 volts, and I just measure the current again, just to be sure. .76. So this means that we are driving roughly 62-63 watts through this Peltier cooler. So then now all we have to do is to wait. But we already see that the back side of this unit, the water cooler block, is 32 degrees. The water is also 30.5. And what I see here, the water temperature inside the tub, 21.2 or 23 degrees Celsius, based on the two thermometers. And then the water in the tank is 30.7, so it's the same as here. And the outlet temperature of the radiator air, that is 29.5 degrees Celsius. So we just wait, and we see what is happening. So I will just quit the recording. The time still stays here, and when the temperature goes down to, let's say, 5 degrees or something like that, then we will see how much time elapsed. and we also see the temperatures and other readings. So let's come back in some minutes. So just a little check-in. As you can see, or hopefully see, the channel 1 is showing 3.7 degrees Celsius, and that is actually a bit closer to the bottom of the tank or this water system, which means that we are almost at the freezing point of the water at that area. And then channel 2 is a little bit closer to the surface of the water, and that is 6 degrees Celsius. So this is the problem that I was talking about, that we don't have any kind of stirring, so we only rely on the, let's say, convection inside the water, which are basically based on the temperature differences between the different areas of the water. So that's how it basically stirs itself. But the problem here is that that's not so sufficient, and the best would be to have some stirring system inside this, but it would be very difficult to introduce it, so we don't do that, and we just do the same, let's say, error for all the systems. So what I do is I leave the recording here. Maybe I will speed it up, but now we are very close. We are 1.7 degrees away from the 0 degrees. So I just want to see when this thing happens, and I also want to see if something happens to the water, if I can see some turbidity or something like that. I cannot see it yet, so I guess the bottom is still above 0 degrees Celsius as well, because usually where the ice starts to form, of course, is the area on the bottom of this aluminium tank, where it is in contact with the cold side of the Peltier cooler. And that of course makes sense, because you have the heat transfer there. But also when we are at in some later stages of the cooling, you can see that the ice starts to grow from the walls of the aluminium tank. And that's because the aluminium is much better heat conductor than the water, and it picks up the temperature of the cold side better, and it conducts to the basically to the sides of the tank, which means that those areas reach the desired temperature earlier than, let's say, the very middle of the tank, or not even the middle, but those areas which are not directly above the surface of the Peltier cooler and further away from the sides. So here 0.0 degrees and 1.5 degrees, and this happened in like 15 minutes. But we will see the charts, that's more easy to analyze. So after a few minutes you can see that the temperatures are still like unchanged. So this is 0 degrees, and then I was checking the temperature here. I could see that it went down below 0 and then it came back to 0, and that means that the forming of the ice started around the sensor, because basically what we directly measure is just the direct area of, or the direct environment of the sensor. So that means that when you have that small dip in the temperature, you basically supercool the water around the sensor, and when the phase transformation starts, so the nucleation of the ice, the solid phase starts and let's say kicks in, then the temperature jumps back to 0 degrees, and then it stays at 0 degrees as long as the wall surface area of the sensor, or the environment of the sensor, is not converted into pure ice. And that's why we could see some temperature jumps. And of course, maybe we are not measuring exactly 0 degrees, there is always an inaccuracy and error in the measurement, but we can still see the trends. And that's important for us, to see the changes. And if we see the changes, then we can have these ideas and we can brainstorm about the things. But I can also see that this top sensor also, which is on the back side, or which is closer to this area, this wire here. That's stuck at 0.5, 0.2. So when I plot the chart, we will see what happened there. But I'm quite sure that we will see something like the chart like comes down, and then there is a dip, and it goes back, and then it continues going as at 0 or around 0 degrees. And I also see that there is some ice forming in the middle of the tub. So we will see what happens in a few minutes. So just a little update again. I see more ice forming in the water tank, and the temperature is still stuck at 0 degrees at this thermometer and 1.2 degrees at this thermometer. So I guess both of them are at the freezing point, but what I have to say that in the channel 2 case, the sensor is not entirely immersed in the water as in the same way as the channel 1. So that can be the reason why this is still a bit above 0 degrees. So the water is not that frozen there, but I see that more and more ice started to grow around the channel 1. And then the backside here is 33 degrees, 33.7 and 32 degrees in the water, and this is also showing this guy here, which goes into the tank, 32.2. So these temperatures pretty much the same, and the air which exits the radiator is 31.2 degrees. So basically the difference is within 1 degree Celsius, because 32.2 is shown here and 31.2 shown here for the water tank and the radiator respectively. So that means that we are not generating too much heat, so the radiator can pass through all the heat to the environment. So yeah, I wait another I don't know how much minutes, and we see what happens. Again, just a little update. So 2100 seconds elapsed, so that's like 30 minutes, more than 30 minutes, and I see some ice forming in the tub, at least in the middle, and the temperature dropped down to 0.3, minus 0.3, and the temperature at the second channel is 0 still. And I also started to see some ice coming in from the side of the aluminium tub. So that's interesting. So let's keep the system running and see what happens. As you can see, we are still struggling to bring down the temperature everywhere and transform all the water into ice. And of course there is a scientific reason for that, and I just want to explain that to you, or quickly tell. So this latent heat is actually a huge amount of energy, and so huge that if you take 1 liter of water and it is at 0 degrees, if you want to warm it up to 80 degrees Celsius, so you want to change the temperature of 1 kilogram of water with 80 degrees Celsius, you need the same amount of energy for that, which is required to freeze the water. So the latent heat is, if I remember correctly, for 1 kilogram of water is 334 kilojoule per kilogram. So that's the same amount of energy which is needed to warm up the water from 0 to 80 degrees Celsius. And that's why we are still stuck here, because we have now, of course, we just need 1/10 of that, 33.4 kilojoule, because we have 100 grams of water and not 1 kilogram of water, but still, that's a lot of energy as compared to the energy which is needed to bring down the temperature from, let's say, 27 degrees to 0. And if we just do a quick calculation, I don't have anything in front of me, or I haven't thought about this, but I just came up with this right now. So if we think about this thing, that we need a lot of energy to bring, we need 334 kilojoule for 1 kilogram of material to bring it from 0 to 80 degrees, or to freeze it. and we have 1/10 of that. So let's say 33 kilojoule energy was needed or is needed to bring this to freeze this water from 0 degrees, right? And we went from 27 degrees to 0 degrees. That took around I don't know, 10-15 minutes, and that is like 1/3 of the energy that is needed. So that was roughly around, let's say, 11-12 kilojoule. So now we can clearly see that the channel 1 is at minus 2.2 degrees Celsius, and that means that the water around it pretty much froze. And I can see that most of the water is now transformed into ice, but I still see that the channel 2 probe, which is this guy, which is not under the water properly, that is still around 0 degrees, and I can also see that that is the probe which is surrounded by liquid water more, while the probe number 1, which is the channel number 1, is like frozen into the ice. So I think I will stop the experiment here, because I've been running this thing for an hour and I still was not able to entirely freeze the water, and that's mainly due to the poor stirring of the water. So of course now we are just relying on the pure thermal conductivity of the water, which is not so good, and then we cannot really do the good evaluation of this. But we could see that the water went down to 0 degrees quite quickly, and we can already use that data to evaluate the performance of this cooler. Of course, this is just one current at a certain cooling system, or at a certain cooling power, let's say. So of course you can change the current, you can change everything else in your parameters. I just want to do the sort of systematic test, so I just use the current which corresponds to the minimum cooling of each Peltier cooler, and then I want to see which performs better, or how do they perform. So now I will do some calculations and show you some charts and plots on the computer, and then we conclude the video. So let's stop the experiments here, because it's getting quite hot, I mean in the room. So let's see what we get from the computer analysis. So after like half an hour I removed the box from this cooling device, and I can still see the ice. So I try to remove the ice for you and just show you how much ice we created. So I put this here, and so you can see this is pretty much ice. I can actually measure the weight of it. So this is precisely 50 grams of ice. Of course, this should be more, because of course I was waiting for like half an hour without doing anything, but I can show you some things with the ice which might be interesting. So I think you can see the shape of this. I hope it melts quite quickly, but this is the problem. So this part is quite thick, and as you can see, this is the thicker part, and this is the part which is above the Peltier cooler. So the Peltier cooler basically transfers the heat through this area of the ice. And then you can see that there is a dip here and a dip here, and that is because that's the area which is like the least affected by the cooling. Of course you have this boundary, because these areas of the water are like directly touching the side of the tub here. But then in the middle, so basically somewhere here and somewhere here, we are far away from this point, which is the coldest point, and far away from the walls. So therefore, since there is no circulation of the water freezes here and here the slowest. So this is basically the weak point of the experiment. And you can also see that here check my thumb, and here, check my thumb, the ice is much thinner. So here, of course, it's the thickest because the Peltier unit is just here. But here and here, which are the least affected areas, the ice is like almost transparent. And then here you can see this hole, I think the thermometer was there. So that was the contact point. And also here you can see this hole here, that was the other thermometer. So thermometer, this was the channel 1. And that's why this showed the temperature as a lower temperature, or reached a lower temperature earlier, because this was better surrounded with the ice, and this was a bit higher because this was closer to the surface of the water. So yeah, so this experiment is of course not perfect, but since I'm testing all the devices in the very same manner, so it doesn't matter how I place them, the Peltier device is always here in the middle. So these will be these two areas where my fingers are the least affected areas regarding the volume of the water. But I do roughly the same cooling method, which means that yes, I'm doing some sort of error because I'm not mixing the water, because yeah, it's just not possible right now. But on the other hand, I do the same sort of error to all of my Peltier coolers. That means that this kind of systematic errors appears in the same way in all the measurements, and it will not bias basically the conclusions, because all of the things are affected in the same way. So that's what we get. And I'm analyzing the data, so once I have the data, I will finish the video and show it to you. So let's just quickly go through the data and learn from it. So first of all, let's look at the performance chart. So since the water temperature was not really hot, I was assuming that we can use the performance chart, which corresponds to the 27 degrees Celsius hot side temperature. We were a few degrees above that, but the curves are not too much shifted. So what we do is our regular exercise. So we check for the voltage and current values. So we were roughly at 4.76 amperes and 12.89 volts. So this is roughly the slope that we are looking for, this black line. And then the voltage is somewhere here. So then we look for the intersection of those two values, and then we see that the dt was really high. So this was, let's say, roughly 62 degrees Celsius, which is very bad, because I always try to emphasize that either we go for really high dt or we go for really high sorry, not here but here, QC values. So in order to reach higher cooling performance, of course we should have aimed for this area, but what I wanted to try here is to see how the device behaves when we apply the same parameters, the same current and the same type of cooling, when we were able to measure the I minimum and the T minimum without any load. So this is basically showing you how important to consider the load, because when we measured the minimum temperature, we had this, and the T min was roughly minus 23 degrees Celsius. So without load, at this ampere value, we could reach 23 degrees Celsius, minus 23 degrees Celsius. So that was this curve when I put the current on this and put the temperature on this, and we measured like different points, and we could see that there is like a parabolic curve. So when we increase the current in the beginning, we could reach lower temperatures on the cold side, and then this is basically these two numbers, the T min and I min. And when we increase the current further, we could not reach or could not get better cooling or better
cold side temperatures, but we got worse. And this is basically the area where your cooling is not so sufficient, and then also the Joule effect appears. So actually, due to the high amount of current that you are pumping through the system, the connections and everything which is conducting the electricity gets hot. And this is basically, this is the point after which the Joule effect like overpowers the Peltier effect, and therefore any kind of further increase in the current will lead to increase in cold side temperature. So we should have aim for this. So in reality, we should do this, but I wanted to see what happens here. So how much we can mess up the, let's say, formulas when we really put some load on the device when we try to replicate these kind of parameters. So unfortunately, if we continue the performance chart, if we draw the vertical line, we end up somewhere here. And that means that we have roughly around 5 watts of cooling power, which is very poor if we compare it to its maximum cooling power, that is roughly 60 watts. So this is like 1/12 of that value, and that's very, very sad. And this is like the output, the heat output based on the wattage. And this is basically the heat output, which is coming from the heat transferred from the cold side to the hot side. So at this setup, the water cooling was dealing with, let's say, 67 watts. So I round up this number a little bit. So 67 watts. That's not too much. It's okay. So these are the curves. As you can see, there are 2 groups. We have this up here, and then these 2 down here. So these are the 4 sensors. And you could see that the higher one, the channel 3, that was immersed in the water. So that goes here. That's so the green curve, and the blue curve goes a bit lower, because that was the air temperature which is exiting the radiator. And then also there is a slight difference between these 2 curves. And if you remember, the channel 1, the black curve, was more, or it was more immersed in the water, so that was surrounded in a better way as compared to the channel 2, so the red curve. The red curve was just slightly immersed in the water. It was more closer to the water surface. So of course that resulted in a bit worse cooling. But you can see that roughly after 16 minutes, we reached 0 degrees Celsius around those sensors. As I showed it with that ice, some areas of the water are not really affected by the cooling, or not in the same way as some other areas. So there is some sort of bias between the different areas because of the positioning of the Peltier cooler and because of the distance from the walls of the tub. So yeah, but if I do some quick calculation, so one detail that we know is that we at this point here, we were feeding like 5 watts of cooling power to the water for 16 minutes. And we also know that we can calculate the heat needed to bring down the temperature from 27 degrees to 0 degrees of the 2 objects. So we have the delta T equals 27. I just write it down. And this is not dt, this is delta T. So the delta T is 27 degrees Celsius. So that's this point, the difference between this point and this point, basically. So this, the initial and final temperature. So we have this. And then, of course, we have the CP, or specific heat of the aluminum, that is 0.9. And then the mass is 87 grams. And this is the specific heat of the water, which is 4.18, let's say. And the mass was 100 grams. And you just do the math and get this. And if you remember my small thought process or brainstorming, I was saying that or I was estimating this value roughly as like 11 kilojoule. And what I tried to say there is that in order to freeze the same amount of water, we need like 3 times more energy. So for example, from this point, if let's say everything was at 0 degrees, then we would need 3 times 16 minutes, so 48 extra minutes from this point to be able to go down and solidify all the water molecules. So here we just at 0 degrees, and then here we are below 0 degrees, let's say. So that is basically done here. This is another calculation which is basically saying that if we have a system which requires like 3.72 watt hours, so you have to feed 3.72 watts into the system for 1 hour to make this kind of, or to give this heat to the system or remove this heat from the system, then we see that 44 minutes is necessary. So 44 minutes is necessary with 5 watt of cooling power in order to go from 27 to 0 degrees Celsius. So what we can see here is that is this 44 minutes. And well, nothing really happens here because this curve here already starts to level off a bit earlier. So there is nothing there, but you can see that here we just get a local effect because just some volume of the total volume of the water gets to 0 degrees, and this should be the time where the total volume of the water, so the 100 grams of water, is at 0 degrees Celsius. But then of course we cannot really see that because of the lack of stirring. So yeah. So what I want to say as a summary, that yes, this test doesn't work nicely. So if we choose these things and try to apply some load, then we will be always somewhere here at the end of the DT curve, and that will result in a very low QC. So the cooling will take a lot of time. But still, I want to see what happens where we are in this area of the I versus T curve, and how the, let's say, capability of the devices show. So this is basically some kind of indication that those videos which try to believe that if you can reach very cold temperatures or with the Peltier coolers cold side, then you have very, very good cooling. But in fact, it's just the opposite. So here, yes, we had more than 60 degrees delta T. So that was here basically. So if there were no load on the cold side, this would have been the case. And actually I did that. So this is measured in a previous video, and this is my own measurements result. And you can see that, yes, we can go down to minus 23 degrees. It's not a problem. But what happens if the system has to do work and has to remove heat? And then we go up to the top curve and we see that, yeah, we reached the minus 23 degrees and our water was roughly 40 degrees Celsius, or our air cooler was roughly 40 degrees Celsius. But yeah, and that also shows us, okay, we reached this kind of DT, but when we look to the left and see what was the QC, then we see it's 5 watts. And you see, you can't even cool down a cup of water to 0 degrees in a reasonable amount of time. Even if we just say that I want to have a glass of nice water, then if we check it, let's say 10 degrees, we can drink that. It's not too cold, not too warm. That is 10 minutes. So even just to take 1 deciliter of water to 10 degrees Celsius took us 10 minutes. I mean, it's much more simple to open the tap and just get the tap water, which is actually somewhere here. So if that is like 3, 4, 5 degrees Celsius. So if we want to get here, we have to wait 12 minutes just for 1 deciliter of water. If you run your tap for, I don't know, 14 minutes, you can get like maybe 100 liter of water or even more. So yeah, so again, this is like a really strong evidence that yes, you can cool down the top of your Peltier device to very low temperatures, but that will not mean that you will cool down anything else to the same temperature, or you will be able to remove heat in a very good way. So yeah, this is the main importance of these experiments that I want to tell you, and I want to show you that those videos which are just measuring the hot side and the cold side temperature and saying that, oh, you see, I can make minus 20 degrees, this is a very good cooler, those are not true. Not in that sort of interpretation. So yeah. So I hope that this was insightful and helpful as well. And you could see that you can mess up an experiment in many ways, and there are a lot of variables that you need to be able to control in order to make your experiment correct, and also in order to make your experiment repeatable and reproducible, because that would be the point of a scientific experiment. So if I do this at home here, and then you do the same at home at your place, and you use the similar things, similar cooling, similar power supply, and similar Peltier device, then you should get roughly the same numbers. Or no, if you idealize everything, you should get the same, exact same numbers. That's the ultimate experiment, when you can reproduce it everywhere, anytime. So yeah, I hope I helped you, and then I will go to the next step, which will be the 8 ampere unit. So see you in that video.